In classical physics, one may possess knowledge of any number of physical quantities to any desired degree of accuracy, provided that you have access to sufficiently sensitive measuring equipment. It turns out that this is not the case in quantum physics. Due to the manner in which physical observables commute, which loosely speaking could be described as the manner in which physical observables are ordered, there will be an inherent uncertainty for some combinations of physical quantities. This uncertainty is not due to a limitation in the technology we have available to us. This is an intrinsic uncertainty imposed on us by the rules by which nature operates. We prove the relationships that we describe in this video in Physics 323, or modern physics. Sometimes when you think about doing math, you might think of something like this, but there is a more abstract way of thinking about how to math. When we math, the first thing we do is define the objects that we will work with and define the operations that we will apply to those objects. For example, back in grade school, some of the earliest math you probably learned was addition and subtraction. The objects that you work with are the numbers, and the operations that you apply on those objects are addition and subtraction. Next, explore. Use the rules and definitions that you described in step one and see what comes out. If you do not encounter any logical contradiction, then you have successfully mathed. As scientists, we want to know about the world around us. However, we have to remember that if we want to know the rules of the universe, we do not have a README file or a manual that describes what those rules are. We are trying to learn the rules by which nature operates while at the same time being part of nature. So all we can do is explore and experiment and observe and see if we could use logic to fill in the gaps of our knowledge and try to come up with a coherent set of rules that describes the way the world operates. So we might ask the question, what is physics? I will begin by saying that I believe nature should behave in a logical manner. I cannot prove this statement. This is just a belief that I possess. It is very possible that nature may possess some inherent illogicalness to it. We may one day encounter a scenario where A is not equal to A, but I do not think that is ever going to be the case. The rules of nature, whatever they are at their most fundamental level, I think will be consistent and logical. Now, from nature's point of view, physics may be thought of as the rules by which nature operates. From my point of view, I might say physics is a model that I write of the rules by which I think nature operates. Think about these two statements. My model of nature will not necessarily be the true model by which nature operates. My model may be incomplete or misguided due to the fact that I have limited knowledge. When I say nature should be logical, I will write my model in the language of mathematics and logic, trying to describe observed phenomena. So the human mind is incredibly creative, and human power of abstract and logical thinking seems boundless. But then again, the building power of nature also appears to be boundless. And in acquiring consciousness at our level, we are able to be part of the universe and then look back at the universe itself. So we will continue and try to learn about the world around us and all the astounding phenomena that we see. So back to the uncertainty principle. One example of two quantities that we cannot have perfect knowledge of at the same time is momentum and position. It is possible to know at some moment exactly where a particle is to 100% accuracy, but if you do that, you will not be able to know anything about the particle's momentum. On the other hand, if you were to conduct an experiment and know to 100% perfect accuracy the momentum of a particle, then you would have no idea where the particle is. Or it is possible to simultaneously know something about the position and something about the momentum, but in doing so, there will always be some inherent uncertainty in your knowledge of both of these quantities. Again, this uncertainty is not due to a limitation in our technology. This uncertainty is imposed on us by nature. These are the rules by which nature operates. Another example of two quantities that have an inherent uncertainty in them is energy and time. As with position and momentum, There will always be some degree of uncertainty in your knowledge of energy and or your knowledge of time. You cannot know both of these quantities to an arbitrary degree of accuracy. One way you could think about the uncertainty principle is to imagine that you had access to some phenomenally precise measuring equipment. You measure the momentum of a particle to a very high degree of accuracy, and after doing so, you could say with confidence that you know that particle's momentum to any number of decimal places that you want. You then measure the position of that particle, again to a phenomenally high degree of accuracy, and you can now say you know exactly where that particle is to any number of decimal places that you fancy. If you were to go back and measure the momentum of that particle again, you might find a new measurement for your momentum that you would not necessarily expect. In a fairly sloppy manner of speaking, you could imagine that performing the position measurement of this particle kind of reset or scrambled part of the momentum measurement, and this will always occur, even for an arbitrarily non intrusive measurement that you might make. This implies that for very brief intervals of time, we may violate energy conservation. From the point of view of quantum physics, energy is only conserved on average. The image on the upper right side of the slide shows an example of energy non-conservation due to the uncertainty principle. This image is a simulation of the large-scale structure of the universe. The bright regions in the image are galaxy clusters, and the galaxy clusters are connected to each other by a network of sheets and filaments of dark matter. In between these galaxy clusters, the dark regions in the image are giant cosmic voids with almost no material in them at all. The early universe was very homogeneous, but there were some regions that were slightly more dense than others due to the uncertainty principle. During a mysterious epoch in the early universe called cosmic inflation, these fluctuations became frozen into the universe. They did not disappear in a time delta t. It was from these fluctuations that all of the particles that make up everything in the universe, galaxies and galaxy clusters, stars and planets, eventually formed. All matter that makes up everything in existence came about because of a fluctuation in the energy due to the uncertainty principle.